Hi everyone. What we're looking at here is a typical buck boost transformer. Buck boost transformers have been around forever. They're pretty old technology now. Really, to be honest, a forgotten technology if one wanted to look at it like that. You can see the input to the transformer through the input coil there is 120 volts AC. Okay, now the output is 90 volts AC. The output coil is connected directly across the input coil. So theoretically one would expect to see 120 volts on the input, 120 volts on the output, but we don't see that. And we don't see that because the coil is wound in such a way that it cancels some of the voltage. Now, how does it do that? How does it cancel some of the voltage? This is one of the tricky parts that's elusive, shall we say. Basically, it cancels part of the voltage because you could say that the inductance is reduced, or you could even say that the magnetic field is restricted by bucking at least part of the total input field. And you've got to remember that it's the time rate of change of the magnetic field, which is the same as the changing current in the coil, that creates a voltage. So the voltage being reduced would normally mean that the magnetic field is restricted in the way that it can change in time, or the inductance has changed in time, and therefore the total, which is the same thing, because if the inductance changes, it means that the total change in current would be different as well. Okay, because inductance is the definition of inductance, I should say, is the ability for the coils, plural, because we essentially have two in parallel here, for the coils to carry a current. Okay, so the current is not able to change in the coils the same as if the secondary coil wasn't there. Now here we have this is a standard wound. This is not a buck boost. This is just a boost transformer, and you can see here the voltage is increased. So how's the voltage increased? We've got 120 volts AC on the input, and on the output we've got 150 volts AC. So what's happening here effectively is that the input voltage is assisted. The current is not restricted, shall we say. There's no bucking of the current, and therefore the secondary coil adds to the total number of turns, which effectively increases the voltage. It's just a step-up transformer, basically. It's one way to do a step-up transformer. Now this is, in my opinion, these basic concepts are absolutely critical to try and understand and get your head around. Now, we've done tons of experiments where we've had bifilar coils with ends tied, where we've seen time and time again where we have trouble getting any voltage out of the end of the coil. My non-inductive coil series, the first 6 videos, went through trying to understand and resolve these issues. So I have gone through a lot of this stuff in the past, but what I want to do today is I'm trying to actually go down to the coil level, to the turn level, to actually see what's going on. So we can see this transformer is a step-up transformer. Okay, you can see there connected in series 180 degrees out of phase. They phase add. Okay, so this is what we've got to think about. We've got phase add and phase subtract. Let's go back to the other one for a second, the other image for a second. Okay, so you can see here phase subtract. Alright, so this is back to our old transformer. This is back to our what we were talking about in the early version of the coils in the series. I'll bring up a picture just a second. Okay, so you can see here, you remember the video 1, primary coil over here, 2 secondary coils, both wound parallel by filer by the very different definition, but one coil is only half the length of the other coil. Okay, so one coil underneath, full length, top coil here, only half the length. We had ends tied up here. Okay, so the current going up that way was the same as the current coming back down this way. Okay, and we had a lot of trouble trying to get any voltage on the end. Okay, and this is a problem because the coils are bucking. Every time you have a bucking effect which restricts, well, I shouldn't say that, I was going to say restricts the current, but technically it doesn't actually restrict the current. What it does is the change of current effectively cancels voltage. You got to remember, this is the tricky part, and this is what they really don't teach you in any basic sort of science class. It's the change of current that creates the voltage. Okay, so if we have a current that's changing, we have a voltage that's changing. As soon as the current stops changing, the voltage stops changing. So we have, again, what we talked about before, we have phase assist and phase subtract. Okay, now the voltage doesn't really have anything to do with current. The magnetic field is current. Okay, and by using bucking coils here, where we have 2 coils that effectively are phase subtracting, so one opposes the other, then that opposition reduces the voltage that's generated. Okay, because the current that is changing in the system is brought down, and we saw that the exact experiment in the video series. What we saw that the input to the input coil, the current was reduced by approximately half. Okay, I think it was a little over half if we had a bucking in the system. Okay, so the input coil over here, the input current was reduced to approximately half when this coil over here was in bucking mode. Okay, so you could say that the bucking on this coil over here reduced the whole system, okay, through the core, because you've got to remember that these coils are all coupled through the core, magnetically coupled through the core, and therefore the coupling in the coils changed the impedance of this coil over here. Okay, the impedance being the DC resistance plus the imaginary number in the middle, and then the AC resistance of the coil together, which forms impedance. So the impedance of this coil over here was changed when this coil over here was bucking. Now I've referred to this in the past as choking the coils off. Okay, and effectively that's what it is. We are actually choking the coils off. So we're restricting how much change in current can occur by restricting the impedance of the coils by changing the actual configuration of the coils. So bucking mode does coil bucking mode does restrict the change of current in the system, and therefore the amount of voltage that can be generated. Now we found a way around it, but what I'm trying to do is I'm trying to go down to the wire level here in this video, and we're trying to have a look at actually what's actually going on to actually make these changes. Okay, back EMF. If you understand back EMF properly and how back EMF works, then it's the same sort of thing. I'll just bring up a picture quickly. Okay, this is what I termed the reduced impedance effect. So when I found this effect, I couldn't find any information on it anywhere. It wasn't documented. I couldn't see anything on it. So I thought, right, well, this needs to be explored and we need to figure out what's going on. So the earliest I documented this effect was back in my guidelines to bucking coils. A very old document now. It's I don't even know, can't even remember, maybe 6-7 years old or even more. Anyway, the reduced impedance effect is the same as back EMF in the fact that the basic effects are the same, but the reduced impedance effect is caused by a different scenario. Back EMF typically is between 1 or 2 coils, okay, and in this case we can see 1 coil. So we can see that as the AC sine wave source is applied across the coil, so the voltage applied across the coil, as the voltage changes, the current changes in the coil. The change in current creates a voltage, okay, which they say induced current here, but the induced current can only flow if there's a voltage that's induced as well, okay. So what's happening here is as the current is changing one way, that change in current between the turns actually creates a voltage on the opposite turns, and the voltage is in opposition to the applied voltage, and therefore the applied voltage is restricted by a current that tries to flow in the opposite direction. Now what's going on here, that this back EMF, if you like, changes the resistance of the coils. So this is typically called the AC resistance of the coils, which boils down to impedance Z, which we go down here a little bit. Okay, so the impedance Z of the coils, so this would be your DC resistance of the coil, plus J. Now you can have plus J or negative J. I think from memory, I think plus J is inductance leading. So typically plus J would be in a mostly inductive environment. I think negative J off the top of my head, now go and check this because I may not be right here. I think negative J is in a capacitive environment. Okay, and then this part here is the AC part. So this resistance number here is the resistance that's, if you like, generated in the coil. So this resistance can change in time as the frequency changes and the obviously other factors, things like applied voltage and all that sort of thing. So there's a lot to it. It's not really that complex, excuse the pun, but it's not really that complex once you get your head around it. It's really just a frequency thing. So the higher the AC frequency, the more voltage which would be generated between the coils, depending on the applied voltage and the current that's going through the coils and all that sort of thing as well. So it's sort of like Faraday's law of electromagnetic induction on a turn-to-turn level rather than a coil-to-coil or transformer sort of level. Alright, so this is what we're talking about when we're talking about impedance and we're talking about back EMF. Okay, so the red arrows and the green arrows oppose each other. Okay, we have in between the turns we have an EMF which opposes the EMF that's generated, thus the term back EMF. Okay, so the applied forward EMF is what we apply here from the source, and then the back EMF is the EMF, and remember EMF is measured in units of volts. Okay, so this is a voltage, the current follows. Okay, so a current can only flow if there's a voltage, so the current then opposes the current. So technically, if you watch some of the Peter Lindemann videos, he does a very good job going through explaining that some of these coils can run on only, or the effective voltage that's actually doing the work in some of these coils can only be, 1 or 2 volts or something like that. The rest of the applied voltage, so if you apply 12 volts across a coil at a particular frequency, the applied voltage across the coil, it might be that only 1 or 2 of the 12 volts are actually doing any work in the coil. Okay, so it's very, very little amount of applied voltage and therefore applied current that actually does the work in the coil because of the back EMF. The back EMF is the problem, at least in some situations. Okay, and this comes back to the reduced impedance effect. The reduced impedance effect, It's a little bit more complex, but when you have multiple coils, okay, 2 or more coils, then the input coil impedance, instead of going down, so that what I'm saying is, in a transformer, when you load the transformer with a very low resistance load, the impedance would go down. The more you load it, the less resistance that the input coil has. And we just recently did an experiment on that. I'll bring that up quickly for you. Okay, this is our thread impedance matching, load impedance matching. Okay, I recently did an experiment. Okay, this transformer here was the test subject. I chose a big one because it had much lower resistance. So we've got 18.8 ohms of DC resistance on the input coil here. Okay, what we did is we just applied a voltage on the input coil, and we just looked at the current with no load on the transformer whatsoever. And this is the current with no load on the transformer. It's a little bit noisy, but at these tiny little low levels, 50 milliamps, most scopes show a fair bit of noise. Okay, so what we did is we took some readings, took some measurements, and we went through and so we measured the input, measured the current and all that sort of thing, and then we loaded the transformer down. Okay, so what we did is we actually short-circuited, so you can't actually see it at this stage, but this red wire here, and it might have been the white one or the black wire here, this, just to give you a bit of a background, this transformer is out of a UPS. Okay, so this transformer is if you like, a push-pull transformer. So this would be connected directly to your batteries, 24 volts in this case. You would have a large MOSFET, sometimes a MOSFET array on these, each one of these wires down here, and it would be a push-pull at mains frequency. Okay, so the output over here would be your mains voltage at your DC chopping mains frequency. Okay. So what we did is we shorted the output excuse me, and then after shorting the output we actually measured and used Ohm's law to calculate the difference. So this is the impedance in ohms. Okay, this is the AC and DC impedance in ohms, 565.77, and that's based on 20 volts at the input and the measured current of approximately 35.35 milliamps. Okay, so what we did after this was we shorted the output down here somewhere. So impedance in a situation like this is the same as V over I, which is Ohm's law. So everyone will know that that's just Ohm's law. Now V over I equals the total impedance, which would normally be the resistance. So down here, to cut a long story short, note 1.5 amperes was what we measured here on the teal trace. Okay, set to 5 volts per division, 20 volts on the input. We used Ohm's law again. Okay, so we got DC resistance of 18.8 ohms initially, but now after loading down the transformer as much as we could, the impedance dropped down to lower than what the DC resistance was, so 12.66 ohms, and that's because we had 1.58 amperes drawn on the input. Okay, so 1.58 amperes compared to what we measured with 20 volts. So what I'm saying is, with 20 volts applied across the input coil and having measured the input resistance, we can find the amperage that will flow in that coil if there's no inductance. So when there's no inductance, we should have got 1.05 amperes, but we didn't. We managed to get it up to 1.58 amperes, and that means obviously that the resistance in the coil at that time is 12.66. So you can see it's changed a lot. So we've gone from 566 odd ohms to 12 ohms just by short circuiting the output. So you can see that a lot of changes occur in these inductive devices depending on the configuration, depending on the coil interactions between each other, and this is the important thing. We've got to go down to a coil / turn level. We've got to look at the turns, what the turns are doing, and back to our original idea, an old idea, is the buck boost transformer. Now I just want to put in a little bit here. My original experiments were the self-oscillation and bucking coils. An old video, most everybody's probably seen it. If not, go and have a quick look. Now I had 4 coils on the machine. It sort of looked a little bit like a meg, and I found that there were certain effects that were visible, but only visible at a certain point in time. Now what I had to do to get to that point was I had to actually adjust the frequency. And to adjust the frequency, what was going on was the coils would become resonant at a particular frequency. And what I did outside the machine, e.g. connecting loads, short-circuiting coils, all that sort of thing, once the coils were resonant, then it didn't affect any of the connecting loads, and short-circuiting coils didn't affect the input. Okay, and that's a really key, really critical aspect. You've got to have these coils resonant to be able to make sure that your input is not negatively affected. Okay, if the coils are not resonant, then as soon as you connect a load, it's going to load your input, which means you just have a normal transformer and nothing's working. Now, recent experiments that we showed, especially in the non-inductive coil series, and we'll go back to that for a second. Okay, this was video 7. Now, by separating the coils, we're having one on the top, this coil that's on the top exactly the same as one on the bottom, the only difference being that we had a 22 turn of roughly about 1.6 millimeter wire on the top, which is just under the black tape there. So effectively we have 1, 2 and then 3 coils. By separating the coils, putting one on top, one down the bottom, and then pulsing the input coil, the coupling, the magnetic coupling, electromagnetic coupling between the coils is reduced. So what we were able to do is we were more easily able to get the coils to interact together without choking the coils off. So what that basically means is the current in the system, the input current and the output current was not reduced quite so much, in the effect that we can still make the machine do work. Okay, so just to reiterate, if you haven't seen this video, the input coil here, we had a 10% duty cycle. Okay, so what you sort of see here on these spikes here is the input. Everything else that's or appears to be flat there, everything else there is when the input coil is off. Okay, so there's no way for current to flow on the input coil, at least from the power source, on the input power source, because the MOSFET's off. Okay, now what happens is the input coil here brings the output coils up to a certain voltage, and then the diodes, we had 2 diodes, then the diodes conduct at a certain voltage, and then the coils are left to do work on their own. Okay, now basically what that means is that really our input coil is really doing no real work in the system. all our input coil is doing is getting the voltage on the output coils up, and then letting the output coils fight one another, if you like, to do work in the system. And if we forward up to here, then you can see the little gap in here is the 10% on time on the input coil, and again that gets the voltage up. So we've got amplitude there. Now this is current, so this is current on one coil here, and this is current on another coil here. Both of these are output coil currents, not input coil. I don't have any traces on the input coil. So what happens, the input coil switches on, it brings the voltage up. Now the conduction of the diodes occurs, and then all of this steep decay time here, okay, all of this decay time here is output. So we've got pretty much 100% duty cycle on the output, but we've only got 10% duty cycle on the input. Okay, now area under the trace, we've got a couple of, or one really good thread from Bendorfer that's going through that. Area under the trace, there's much more area under the trace for the output as what there is on the input. Now anybody that is familiar with this sort of thing should know what it means. Basically, there's a lot more work going on between the output coils than what there is between the input to output. Okay, so we still have output when the input coil is on. The output's still there, but because the 2 or 3 coils are all working together, okay, we get the voltage up as high as we can, switch off, and then that's it. The input coil's done. Let me try and find a better photo of the coil. Alright, hope you can see that alright. Okay, so we've got, you can see this is the input coil out the back here. Yes, I should have snipped all these little coils here a bit shorter. At the time it was just a quick experiment. Anyway, input coil here, output coil, you can see with these wires, output coil here with these wires. Now you've got to remember that these two output coils work together. Okay, so we've got an asymmetrical system. So what I mean by asymmetrical is there's 3 magnetic fields all working in time. Now Floyd Sweet told us this isn't really important. Let me bring that up. Okay, this is one of the old original documents. This is one of the ones that was scanned, put up onto the web early on. I was very kindly given the original documents in a anonymous package that was sent to me, along with a whole bunch of other documents which are all on my website. Now this is Floyd Sweet's handwriting. First of all, we had very recognizable handwriting. So I've verified this. Floyd Sweet, this is Floyd Sweet's handwriting. The space quantum modulator, how it works. First, a time varying magnetic flux must be produced. That's critical. And we know that's critical from where? From Faraday's law of electromagnetic induction. Now Floyd was a genius. He knew all that stuff inside out. Okay, I can verify that. I mean, there's places that I've read stuff from Floyd Sweet that I've not read in any science textbook. So he was well above the average level of the average Joe when it comes to science. Now this next sentence is really critical. You've really got to read between the lines here. It's really easy to read this sentence and just glance over it and not think much of it. This must be caused to vary in sync with 3 modulating signals. Okay, what are the 3 modulating signals? Okay, this is critical. Asymmetrical. You got to think asymmetric. Why not 2 modulating signals? Why 3? Okay, now this is the part that is not clear. He said the 3 modulator signals are displaced in time phase 120 electrical degrees. Now 120 electrical degrees would typically be 3-phase power. Okay, so if you were to think about a three-phase generator, each phase would be 120 electrical degrees. Okay, but that's not what the space quantum modulator was. Okay, the space quantum modulator was a single phase energy producing machine. Okay, so what we're reading here and what the facts and everything are, shall we say, I think there's more being said here in this sentence than most other places, full stop. Okay, the magnets producing coherent quantizing of the incoherent quantum packets comprising the surrounding space field, the space field that we live in, providing a continuous stream, a DC stream. Okay, it doesn't change in time. There's nothing that the magnets were doing. Okay, I don't care what anyone says. A continuous stream of energy. There's nothing about continuous stream of energy that says anything was done to the magnets whatsoever from an infinite source. I want to point out magnets typically are a DC magnetic field. Okay, well, this we all know. This is pretty much standard sort of science. Everybody knows that. Now, I've done the experiments before. It doesn't matter how much waving of the magnetic field that you do. If all the coil is underneath the magnetic fields from the magnets, which all Floyd's devices were, it doesn't matter how much the field waves. Okay, electromagnetic induction will not occur according to the Tom Bearden theory of magnet conditioning. Okay, if the blade is waving, remember all that sort of stuff, it's not going to produce voltage. Okay, Floyd Sweet says here, as the time varying flux of a period of 1/400 or 2.5 milliseconds times 10 to the 3 or 2.5 milliseconds sweeps over the stationary armature coils, voltage is induced. Okay, and that's technically not right. Now, what I do want to point out here, I think it's probably a bit early to say too much, but the magnet's continuous stream of energy is the flux. Now, if we had 3 modulating signals, then at least at the very minimum, one of those modulating signals would have to be in opposition to the magnetic field of the magnets. Possibly 1 or 2 would be in addition. Okay, now there's more to it than what I'm saying here, and I'm not going to say too much because it's way too early for most people, but that's something that we need to start thinking about. So what I'm saying is, as the magnetic field of each coil, and he's talking specifically 3, and we know from Floyd Sweet's diagrams that he did per unit, there were 3 coils. There was the bifilar output coils, okay, and technically they're not bifilar by definition, but because there's 2 coils, so they called them bifilar back in those days. And then there's a feedback coil. Okay, there were coils on the outside which were called drive coils, but they were at right angles, and technically they wouldn't really have a lot to do with the actual operation of the 2 primary output power coils or secondary output power coils. So what I'm sort of saying here is one of the 3 coils must have had an opposition to the magnetic fields of the stationary space field here of the magnets. Okay, so the continuous stream of energy from the magnets must have been interrupted, shall we say, by at least one of the coils that had a signal on it. Okay, so read between the lines there. There's more to it than what I'm saying, but I'm not going to say anything more at this stage. It will just confuse some people. Just to reiterate, so we've got power coil here, okay, we drive coil over here. Now this is the Walt Rosenthal version, so the shall we say the drive signals for the coils was done on this transformer here. Okay. On the other version we had a separate coil for each drive pair. So this is one drive pair, this is another drive pair, they work flip-flop, and the coil was coupled, each feedback coil on the other diagram was coupled directly to this. Okay, that was the later version of this diagram. So Floyd went through lots of different tests and ideas to perfect his machine, and this was prior to that, which is this one here. So this feedback coil here, this feedback coil was the if you like, the primary coil, primary signal source of these two coils here. Now remember that this is a pair. Okay, so when we were talking about the three signals, we've got signal 1 here, which is the arrow, signal 2 here, which is this arrow, and signal 3 here, which is not shown by an arrow. Okay, but all these coils work together. Okay, so we've got 3 signals here, and at the same time over here, but in a different area, and that's the critical part, different area, we've got 3 signals over here as well. And again, this is flip-flop. Okay, you can see it's flip-flop because arrow here is opposite to the arrow here. So we've got current moving up this one, but down this one. Alright. So again, back to the point, at least one of these signals in this pair here would oppose the magnetic field from the magnets, which is a DC source, but could be made to be AC by the coils. So I want to come back. Look, Terrio Caponazzi, he is an absolute legend. He's one of the originals back in the early days. He probably wasn't too far after Floyd's Suite. His ideas are instrumental for all of humanity. He's shown lots and lots and lots of working machines. Unfortunately hasn't really been too forthcoming about operation or anything like that. As far as I understand, he sort of tried to hide a lot of it and possibly even sometimes confuse it. I don't blame him. You know, it's a pretty difficult world out there. You know, he's got to protect himself, so I don't blame him in that regard. But in saying that, what he has shown has been instrumental. Okay, now this comes back to my video series we're showing before. We've got coils which are wound back on themselves. Okay, we've got coil 2 layers here, okay, which are wound counterclockwise. So 1 layer, 2 layers counterclockwise. Okay, and then he brings the wire up and then he winds clockwise. So these coils up here are all clockwise. Now if we go 1, 2 layers counterclockwise, then we've got roughly 1 layer if we add these two together. So 1 layer plus another half a layer if we add these two together. So 2 layers versus 1 1/2 layers, which would be the same, technically the same as what I showed in my image before. So we've got roughly about half a layer difference between the 2 coils here, and that half a layer difference, believe it or not, is this distance here. Okay, so we've got a half a layer that is actually inductive here, or at least half the length, which is at least inductive here. Okay, so at a wire level, within this coil at any one time, there is a percentage of the current that is flowing back on itself, which comes back to our first image in the video, which is the buck boost transformer. Okay, so this is by definition, and this is by every means that you can think of, a buck boost transformer. Now what the critical key and aspect is here, and Ruslan especially, Ruslan, I've got the greatest respect for Ruslan, top Ruslan, most people might know him as. When he's been showing his machines, he talks all the time about resonance. It's got to be at resonance, and it does have to be at resonance for the reasons I explained prior in the video. If the coils are not in resonance, then when you load the output coil, the input will be loaded. Okay, so you've got to have resonance so that the input's not loaded. Now the spike, there's a couple of things that happen here. The driving of these coils, you can break the driving of these coils down to a very simple set of circuits. Now this is the original Tesla circuit, and Dario Capanazzi said that he worked off the Tesla patents. Okay, so this basic circuit here is instrumental in the operation, and we know for a fact that this push-pull circuit is instrumental in the operation. Effectively, this could be here replaced the AC source. Okay. Now the secondary coil here is basically just this coil here. Okay, so this is Tesla's secondary coil. He's got counterclockwise and he's got clockwise turns. Now at this stage, remember the voltage and current are different. To get more energy out of a machine, we need to generate excess current and excess voltage. Volts times amps equals watts. Input watts, if you want output watts greater than input watts, we need more. So we need to be able to do some work. Okay, work being magnetic field pumping current from the source, pumping current, pumping electrons, all that sort of thing. Okay, so this buck boost transformer here, if it was resonant, then at a resonant point, the voltage would be at its highest. The amplitude of the voltage would be at its highest. Okay, but because we've only got effectively half a length of wire here that's different. Okay, remember we've got 2 turns to 1.5 turns. So we've only got part of this that's inductive. So the problem again, as we've seen before, is getting the voltage up. Because we have a cancellation, and the voltage is going to drop. Okay. So for each piece of wire, for each turn, there's a cancellation of current because it's buck boost of 0.75, I think, if you do the math on that. So it's roughly cancelled by 2/3. So I think at this stage, I think the spark gap is probably what we want to look at here. So Dario Capanazzi used a spark gap, and he used the spark gap on the end of this very, very low resistance, because it's spaced out, or have very low AC resistance, very low impedance coil. So this spark gap potentially it's a switch, okay, a very fast switch, and this is the spark gap here. Okay, now this circuit might be slightly different. Okay, I'm not saying that this circuit is exactly the same. The circuit might be slightly different than what Dario Capanazzi used, but the basic idea is the same. So here's a transistor here, here's a transistor here, and those transistors are there and there. Okay, driving a push-pull circuit which replaces the AC mains. Okay, this is handy and useful because you can tune it to the resonant frequency that you would use. Now a lot of Dario Capanazzi's machines, a lot of them were 50 Hertz, believe it or not, and Russlands are quite different. Russlands are about 37.5 kilohertz, I believe. So the resonant frequency is quite different.
Привет сразу Кирилла и Олегу снимаю. Олег, смотри, значит, ну вот она, вот эта херь, это то, что там показывалось. Видишь, они там выступают, и это все, вот оно. Смотри, я сейчас вот перемотал большую катушку, как я тебе и говорил. Вот щупы, вот он индуктор, и вот кондеры. Частота 25 кГц, вон там показ этого генератора. И вот здесь, смотри, на индукторе тоже вот они, выступы идут. И сейчас смотри, что сделаем. Сейчас мы это сложим. Вот она. Вот она фигарит, волна стоячая. Вот она. Короче, все работает, действительно, так оно и есть. И если чуть-чуть частоту, хоть чуть-чуть сдвинуть, вот смотри, что происходит. Такого не было никогда, я тебе точно говорю. Вот смотри, сдвигаю частоту. Все, пиздец. Вот, обычная синуса как бы валит, и все. Смотри. Увеличиваю частоту. Точнее, уменьшаю, делаю как надо. О, смотри, раз. Меняется все офигенно. Обрати внимание. И вот она красота эта. Вот такая хрень. Надо сейчас подключить сюда, посмотреть, что будет. Олег, показываю тебе, Кирилл тоже, да, заранее. Значит, смотри. Подключил к генератору. Вот генератор работает, смотри. Вырубаю этот нахуй. Все. Никуда не подключен. Вот щупы. Смотри, что происходит. Съехала немножко это самое. Генерация съехала. Вот они. Вот они, эти рыбки. На вот этом выходе. Вот, осциллограф здесь стоит. Вот он, щуп пошел. Тут изолентой просто прижал, чтобы... блядь. Чтобы это все... Ну, убежало все-таки все равно. Вон, смотри. Это все работает от него сейчас. То есть с 3 витков можно вообще делать не с этой, не с горшка, прям вот как я сделал. Здесь напряжение высокое получается, а просто с 3 витков. Сейчас он, блин, видишь, какой он тут. Частота ушла. Смотри, сейчас я подстрою. Смотри. Беру, подстраиваю. Вот. Смотри, что происходит. Смотри, вот. Ничего. Обычная синуса. Надо поймать этот эффект. Вот он. Вот он. Короче, вот эту вот хуйню и надо поймать. Вот она. Во. Короче говоря, вот так она и работает. Потребление. Видал? Так, сейчас еще подстроим немножко, блин. Что он тут, блядь, глючит. О. Это мощность. Это скважность я сейчас делаю. Ну, ток вырос, конечно. Смотри, что происходит. Вообще пипец. Ну, 4 ампера потребляет. Но, кстати, стрелка колеблется постоянно под эту вот всю мутатень. И если я сейчас уменьшаю скважность, смотри, 3 ампера потребления, как у меня и потреблялось. Смотри, что делается. Вот она. Вот это правильная намотка. Действительно бифиляр встречный. И, кстати, греется здесь. Вот в этом месте нагревается. Вот я тебе точно говорю, Олег, нагревается в этом месте, прикинь. Пиздец. Вот она. Вот это и надо получить, вот этот эффект. И это факт. Понимаешь? То есть сейчас, если скрутить, точнее развернуть эту синусоиду, вот она. Она здесь не пляшет. Как-то так, да, вроде бы. Не видно. Надо снижать эту самую. Ну, пляшет, вообще пляшет. Кажется, что синус чистый. Нифига не чистый. Вот они. Вот она, стоячая волна. Ну, будет она у меня работать? Что как частота увеличилась? Не пойму. Вот так вот.
What I sort of want to say at this stage is this arrangement has a lot of benefits, but a lot of bad things as well. A lot of positives, a lot of negatives. Negative is that finding the resonance, finding the proper resonance, is, in my opinion, quite difficult. And then once it's resonant, then making sure that the input and output voltages are sufficient to be able to do to get this coil to do any work. That's the hard part. Once you have resonance, and once you have the turns on your transformer here and here right, then the output voltage here on your output coil will be right as well. But getting to that stage is quite difficult. There's a lot of work to it, a lot of fiddling, a lot of messing around. So I think that's sort of really what I want to say. And at the end of the day, these machines are all the same. They're all exactly the same. It works on magnetic fields opposing each other, getting your voltages up. Now once your voltage is up for the same resistance, your current's going to go up. Okay, so as it generates more current, as you increase your voltage, it's going to generate more current. And because you find that resonance point, when it's at resonance, the resonance won't affect your input. Okay, so your input, and this is the key thing. And like I said, these machines are all the same. They all work on the same basic concepts. They might look different. There might be lots of different ways to get to the same end result, but the end result is always the same, and it can only ever be. You've got to remember, like if inside the coil there's billions and billions and billions of little magnets, how do we get the magnets to move? The same as the magnetic rail gun that I showed you the video. Okay, so we've got to put those magnets under pressure, and we've got to fire them out the end of the coil, as if the little electrons, being the magnets, as if the electrons are under pressure, so that we're firing them out the end of the coil. So like Don Smith said, these are electron accelerators. That's exactly what they are. We accelerate electrons down the end of the wire. Now they're all the same. All these machines are exactly the same. You've got to stick to the same basic concepts to make these things work. Okay. The difference between some of my machines and the Terrell Capanazzi machine is, the only difference really is magnetic coupling. Okay. My machines, most of them have all used two separate coils. Okay, so they might be spaced out on a transformer, which you've already seen the basic layout, and the two separate coils interact via the core. Okay, so that means we can get the voltage up to a certain degree without starving the coils off. It's just a little bit easier to work and learn with, because like I said before, these coils can be quite tricky. So at the end of the day, this was one of the first machine, or this is actually a replication of, this is the video of Terrell Capanazzi's early machine. This is what it looks like. Basically his replication is very, very well done. Whoever's done this has copied the replication to a T. The transformer looks exactly the same, everything looks exactly the same, so it's very, very good replication. So this is what it looks like. Obviously the grenade coil here, Terrell Capanazzi had other resonant coils in here, along with the pulsing coil via the spark gap here. Okay, so all the wiring, all that sort of thing, it might be really hard to follow, but the basic circuit, and Terrell Capanazzi said he followed Tesla's patents, so the basic circuit is not going to be far away from this here. Okay, if you replace the AC source with push-pull transformer here with a couple of MOSFETs, and you might need a reasonably large ferrite core to get the pulsing going, so that you're not saturating the core and doing all sorts of yucky things. Obviously you've got to get this transformer working at the maximum efficiency, so you're going to need a reasonably large sort of core here to make sure the core doesn't saturate at a certain power level, certain wattage. Now it's possible this transformer here, I don't know this for sure, okay, I haven't seen inside this box here. It's possible this transformer here is that transformer there, because remember what I said before, Terrell Capanazzi, most of his units were at 50 Hertz, so a large transformer like that would be fine at 50 Hertz. It wouldn't be okay at say 37 kilohertz. So 37 kilohertz, if that's what you want to do, that would need to be a ferrite transformer, which is the same as what Ruslan shows many times. Now it's interesting to note that in a lot of Ruslan's machines he used from a very small transformer, which we never really saw working, and increased the size up to quite a bit bigger, 3 or 4, even 5 times bigger, on some of the other transformers, the ferrite transformers, with much heavier gauge turns on them. So that was interesting to note. Some of the smaller ones we never saw working in some of his machines. Now I want to point out, if you go through and watch this video, this guy shows a working machine here. Most of you have probably seen this video, but if you pay really close attention, even though he says that this is a Terrell Kepenazi device, these two coils are separate. If you watch really closely, these two coils here are separate coils. Okay, so this guy here has learned by doing what I've done, and what he's done is he's separated these two coils out, and he's got one that's clockwise, he's got one that's counterclockwise, separated by a very small gap. If you have a look at the black coil in the middle there, I found it a little bit hard to actually follow that back, but the black coil in the middle there appears to be either the spark gap coil or possibly the drive coil. Okay, so he has done what I've done. And remember, this is all about coupling, it's all about the change of magnetic fields. Why do we wind clockwise, counterclockwise? I mean, the first thing that comes to mind is to cancel the magnetic field, but there is more to it. Okay, there's more to the clockwise, counterclockwise. What you got to realize is that the coil, as it carries a current, the current creates a magnetic field. The magnetic field has within the structure of the magnetic field the magnetic A vector potential, which has a curl and it has a magnitude. Okay, the magnetic A vector potential, if you have a very close look at it, each magnetic A vector potential has a curl which has a direction, which would be either clockwise or counterclockwise. Now, as the coils interact with each other, each coil carrying a current, and in this situation we have clockwise and counterclockwise, the coils that carry currents, each one of them would have an associated magnetic A vector potential, which would also have clockwise and counterclockwise fields, and that is quite important to think about, in my opinion. The point of this video was to look at the coils themselves down at the wire structure. Okay, remember, each wire that carries a current, the current will have a direction and a magnitude. The current creates the magnetic field, okay, and the change of the current creates a voltage. So every time we see a changing current, which is the same as a changing magnetic field, then that will create a voltage and an associated conductor that might be adjacent. Alright, thanks again everybody, stay well, stay safe. This video really is just to try and get people thinking about the coils in a little bit more depth and detail.